Hello ladies and gentlemen, welcome to our first instance of our Introduction to Multiparameter Model series. So our second topic covered on YouTube in our data analytics lectures, and today we will have some stuff about matrices and we will be discussing the multivariate normal distribution. Multivariate normal distribution is very important for any applications regarding statistical modeling because very many things can be modeled with multivariate normals. Multivariate, that is many variables distributed by a joint normal distribution. Normal distribution which is defined using vectors and matrices. So let's look at how it looks here. So considering our normal distribution, it is very similar. We have again definition of mean and in this case a covariance matrix. In a one-dimensional case or univariate as it's called in statistics, we have mean and standard deviation or variance. In case of multivariate normal distribution and multivariate normal likelihood, we have the normal distribution which is dependent on the vector of means or a mean vector and a covariance matrix. And this covariance matrix is a positive definite matrix, and it is presented here in a form of a quadratic form. So as you can see, distribution is consists of the determinant of the covariance matrix up to the power of minus n divided by 2 times exponential function of a sum of quadratic forms on the inverse of the covariance matrix. Of course, because here's a sum, it can be expressed as a product of multiple exponents of corresponding to single dimensions, which each exponent is of the exponential function is of the quadratic form. And this representation is has form using trace of the product of matrices of the inverse covariance matrix and the S0 matrix, which is again sufficient statistics. So this is the sum of such outer products of vectors I minus me and its transposition. So generally we use multivariate normal models in case of existing relationship between our measurements or existing relationship between our parameters. So we have a situation that our parameters depend on each other, and multivariate normal distributions are useful to capture certain relationships of this kind. Most known application of multivariate normal distribution is of course Gaussian processes, which we will be covering later in this course. In situation when we know the covariance matrix and only the means are unknown, the situation is relatively simple. We have a very easily used conjugate prior for me, and that will be which is also a normal distribution. So using our prior for me, which is given by a multivariate normal with certain me0 mean and covariance lambda 0, we get our posterior in a very nice form, which again is expressed as which can be expressed as as a multivariate normal distribution conditional on parameters me n and lambda n. And me n and lambda n coefficients can be computed using our measurements and our prior information. So me n can be expressed as a multiplicity of certain matrix or as a solution of certain linear system of equations. In this case, so using both inverses of lambda 0 and sigma matrices, and using sufficient statistics, which is the mean of our multivariate measurements. And new covariance matrix of this posterior is given by lambda n up to inverse of lambda n is given by sum of inverses of lambda 0 and covariance matrix multiplied by n, where n is the number of our measurements. So the situation is very simple, very easy to handle, and because of that we can easily compute the posterior distribution. But life is even more easy because we can marginalize the distribution very simply. Because the issue with marginalization is that we sometimes lose the analytic solution, or we lose the convenient form of the posterior when we marginalize. In case of multivariate normals with known covariance matrix, we can easily split our vector of means to the subvector of means of interest and mean of nuisance, and our vector of parameters of interest is also its marginal distribution is also normal. So assuming that our marginal distribution for mu1 conditional on rest of is normal, and using marginalization we obtain also the normal normal marginals. What is even simpler, posterior predictive distribution for known sigma is also normal. So this is again a very convenient situation, because it is again a product of two normal distributions, because our we are sampling for a likelihood conditional on mi and sigma, and to use it that we need we get a distribution on mi, which is conditional on our mi n and lambda n, which we have computed earlier. So generally the case of known sigma is very easy. We can even compute analytically conditional expectation and conditional variance, which is very convenient for our situation, because then we can easily get the summaries of posterior predictive distribution. So the case of known covariance is very, very simple. Unfortunately, not that realistic, because even if in one-dimensional cases we sometimes can measure variances or standard deviation of our measurements in certain situations, for example by performing calibration experiments. With covariances it's much more difficult, and getting the proper the estimate of proper covariance matrix is a special problem. For those more familiar with automatic control, this is very similar case to the Kalman filter. Kalman filter is a very effective way of filtering the dynamical systems from noises and estimating unknown states when a system is under disturbances. However, we need to know the noise parameters, and especially covariance matrices, because usually we can assume that means are zero and of the noise signals. And in situation when we have the unknown covariance matrices, then the situation becomes much more complicated. And this also happens here because we can do something when we have the unknown mean and variance, but it becomes much more difficult. In particular, the problems start to occur during the formulation of conjugate prior distribution, because such distribution exists. It is a so-called normal inverse Weishart distribution, which is a known distribution, so it's implemented in software, and it can and it's a distribution that's dependent on multiple parameters, mi 0, lambda 0, kappa 0, eta 0, and all those parameters are used to construct this distribution that is somewhat similar to multivariate normal. Posteriors, after time through multiplication, are also the same family, so we don't have any more normal distributions. We have the inverse Weishart distributions, and non-informative priors for that we can obtain by modifying the coefficients of the use of rhythms eta 0. However, normal inverse wildcard distribution is very inconvenient for any computation, especially for more advanced computation in higher dimensional, because the main problem is that we need to sample our for standard computation we need to sample the covariance matrices, and those covariance matrices are positive definite. That's one thing. The second is they are relatively unbounded regarding the coefficients. So they can be arbitrarily large, and that can be a problem, because that might lead to a situation when matrices sampled from normal inverse wildcard distribution will be close to singular matrices. And as you can see in multiple places, the inverse of covariance matrix appears. This is not something that is unavoidable. We can do a computation that won't need to inverse matrices. However, if that matrix is singular, that computation also will explode numerically. So we'll have very large values that will be very problematic to use. That's why normal inverse wildcard distribution is not much used nowadays in modern computing, and the problem of estimating the covariance matrix is being reformulated to the problem of estimating the correlation matrix. And correlation matrix is a nice concept of kind of scaled covariance matrix, because this is correlation matrix is a matrix that has ones on the diagonal, and outside of the diagonal has covariances between variables depending on the index, for example, first and second, first and third, divided by standard deviations of both of those variables. And this is very convenient, because that allows us to this takes us values from -1 to 1. So we have a standardized correlation. So either it's a linear positive relationship or linear negative relationship, or something between. So this is the very convenient situation, because correlation matrix is bounded. It is still positive definite matrix because it has to. It's still symmetric matrix because it has to, but it's bounded to -1 plus 1 coefficients. And we can very easily reconstruct the covariance matrix from correlation matrix by performing following multiplication. So by multiplying it on the left and on the right with the matrix with variances on the diagonal. So that's or standard deviations squared. So why is that better? Because there exists a very nice prior for correlation matrices, which is called an LKJ prior from the names of authors Lewandowski, Kurowiska, and Joe. And this is generally, in very broadly speaking, generalization of beta distribution, because we have bounds on -1 plus 1, so we have bounded elements of the matrix, and with requirements that this beta distribution fulfills the structural requirements of correlation matrix. And this is the realization of this this distribution is much more complicated, how to sample from it, but this was developed algorithm in the famous paper. So this is a relatively recent development. This prior was developed in 2009 with an entire class of methods, and generally this is the distribution of positive definite symmetric matrices with unit diagonal, which are parameterized by parameter eta, and it assumes certain distribution of determinants of this matrix. If eta is equal to 1, then we have uniform distribution of correlation matrices. But as remember, as with uniform distribution of simplexes, this doesn't mean that all the coefficients are uniformly distributed. It only means that the matrices are distributed more evenly. If eta rises, so it becomes greater than 1, then our prior looks more like an it's a multidimensional distribution. However, its mode, the maximum value, is at the unit matrix. So we have the most mass is gonna of probability is located around the uncorrelated variables, and the tails are representing the possibilities of multiple correlations between variables. So the higher the parameter, the more focused, or the more emphasis is put on the variables being uncorrelated, which is again very useful in certain cases, because if we would like to create a model that allows us to get the to move from uncorrelated variables to correlated variables, this is very easy, because using this distribution, we can choose parameters in such a way that assuming that assumptions of our model will be thrown away from being overfit, from becoming too complex, because our prior will say, okay, we think that variables it's still possible that variables are uncorrelated. So let's data provide us enough evidence that this correlation is happening. This is similar to the concept of penalized complexity priors. So the prior that allows us to stay at the uncorrelated variables. And what is the problem with this formulation is that it is not really used. What is used is certain numerical reformulation of LJ prior, because generally when using positive definite symmetric matrices, we really don't want to use them in the full form. Why? Because that is usually numerically much more sensitive. Those matrices, while have certain structure, still have a problem that certain numbers are being the condition numbers of those matrices can be very high. It is much easier to work on the cholesky factors of those matrices. Every positive definite symmetric matrix has so-called a cholesky decomposition. This is an analog of LU decomposition, or in other words, Gaussian elimination of matrix that allows us to invert it or solve the system of linear equations. In case of positive definite matrices, using cholesky decomposition is faster than using LU decomposition, because it's generally works as doing LU decomposition both from top and the bottom of our matrix. So this is an algebraic transformation which requires in general n cubed multiplications. However, we can reformulate LKJ prior into this form by using by standard transformation of variables in probabilistic context. So by reformulating the determinants and using the Jacobian of transformation. This Jacobian is rather complicated. Jacobian, so it's a determinant of the Jacobi matrix in this case. You can find the precise formulation in the Stan manual, where it is fully described how this computation is being done. However, it is also you can see there that because the formulation because our matrices are triangular, this determinant is much easier to compute, and it can be expressed by the coefficients of the Cholesky factors of our matrix. So this is all fine and nice, and so let's see how it works in an example. And we have a very simple artificial example, so no units, no values, working on numbers. And here is our example of estimation of covariance matrix. I've pre-computed this one for large amount of data because it took a bit of time to be computed. As you can see, it's like around 60 seconds per, 120 seconds per per chain, but we will see in a moment why. This is standard stuff, so no need to discuss it. What is our model? Our model, we will be focusing on supplying of taking multiple samples from multivariate Gaussian distribution without assuming that mean is equal to 0, because that doesn't make much difference in what we want to do. However, we don't know the covariance of this distribution, so we will be sampling for our distribution provided with data, which will be an observation with j-dimensional distribution, and we provide with vector observation, and we for easy of representation we just focus that 0. We need a vector of zeros, so we have 0 of our distribution. So what we have here, we have our parameters will be cholesky factor of our matrix. So we won't be working on parameters of our covariance matrix. We will not doing decomposition. We will be modeling the cholesky factor, which will be then used later to reconstruct our matrix. And we will need a vector of variances or standard deviations that will be put on diagonal. And it is already prepared that we don't have to do this computation much more difficult way. We just have the multinormal cholesky distribution that can we represent our distribution. So it will be computed directly using cholesky factorization, so it will require less computation time. Because if we would have to reconstruct the covariance matrix per iteration, that would be very time consuming. We assume exponential distributions on sigma, and we assume the LKJ prior for cholesky factor with the parameter eta equal to 10, which is rather uncorrelated variables. As the generated quantities, we will just generate the correlation matrix and the covariance matrix, because it will be easier for us to see them how they behave, and they are much more interpretable when we are considering either correlation or covariance matrix than the cholesky factor, which we don't see anything from the factor. So we compile our model, and let's generate some data. We get some random seed, and we have our correlation matrix that provide us with a correlation of 0.3 between first and second variable, 0.2 between first and third variable, and 0.1 between second and third variables. So we have our matrix. We have diagonal of standard deviations of 1, 2, and 3, and we get the our distribution our variances. And our covariance matrix is given by this product here. So we generate 5,000 samples, and this takes some time to fit, so that's why I won't be showing it live, but I wanted to show you how it can get nice with a lot of samples, how the estimate can get more precise. So we generate those samples, we generate our vector of data for Stan, and we perform a sampling of our model. We get some communicates that can be surprising if you look at them for the first time, and that our coefficients for LKJ for cholesky factor of correlation matrix are getting not a number. However, when you look at it more precisely, those are numbers that are really in the upper triangular part of lower triangular matrix. So we don't have to care about that too much. So we can ignore those information about it, because it considers structures that we are not that interested in. And we can get now extract parameters from this matrix, because our correlation matrix is a matrix, and we receive the vector as a sum of the vector of my matrix or the table of matrices, so we have to properly extract elements from it. And doing some shifting with plots, we have our distributions. With black, I've marked the true values of parameters, and here we can see what is going on. So our variance matrices are here. As you can see, they are rather well located in the center, even if mean is not exact. We are well in the confidence interval. Same with parameters of omega matrix. Plotting those, we can see the confidence intervals. For those, you can see those confidence intervals are rather thin and parameters are close, but these are parameters of correlation matrix and the variances. So would be nice to check how the actual covariance matrix behaves, because how those parameters are being moved to that end, we can observe the mean of that covariance matrix by getting here the values, and you can see they are rather close. There is biggest errors on the largest element of that. Actual covariance matrix has 0.6 outside of diagonal and the squares of sigma, so 149. And here we have the distribution. We have our matrix that is by averaging of our samples. So situation is very simple. If we provide it with much lower number of samples, the sampling by itself will be very fast, but it will take some more. Our results won't be as precise. So we get our results. The checks will say us the same again about the elements of correlation matrix. If we get our parameters, as you can see, we are not that. We still have rather thin confidence intervals, and we are located with them relatively with them, except for omega 1,3 when we are a bit outside of mean probability mass. And as you can see here, this is the last two of them are a bit on the boundary of what we really values of wanted, but again we've provided it with very little samples, so we didn't have enough information for our model to get the inference right. And in covariance matrix it's actually not that bad, because as you can see, while the parameters of covariances are not that well estimated, here we have the covariance entire covariance matrix is rather stable. The coefficients are close to 0.6 and diagonal is relatively close to what value we wanted. So we'll finish this short part here. The main thing that I wanted you to see, that what we are doing here, we can work on multivariate Gaussians, we can use the LKJ prior, we need to remember about certain numerical properties. So that's why we are using cholesky factors, and in order to work it more efficiently, we'll return to multivariate Gaussians later in this course. But that's enough for this video. In the next one, we will work on more extended example of multi-parameter model that consists of multiple blocks for from different applications. So thank you very much for listening, and see you next time.